licenses.
Well,
Yeah.
like if you bring your own scopes or somewhere to plug in?
To power
Yeah,
electricity outside, yes.
yeah, outside.
If as long as it's available, yeah, there's like 4 or 6 outlets that are available.
So he's retiring. Yeah.
But it's only when
no.
we're there, so that the power shut off, we turn it on. So you can't
Yes,
go all the way
for this Saturday.
Okay, folks,
So
it's
you gotta get there early.
it's just a little bit after 7, so welcome to the September 2025 HAL monthly meeting. If you are online and you have any questions, I think I can hear you. I heard you a moment ago confirm that you can hear us. And we'll go ahead and get the program started. So the first thing that we like to do is to see, are there any new members or people who have not? Welcome. Would you like to introduce yourself?
Yeah, yes. So yeah, my name is Juan. I'm an architect by trade, and basically I just got into astrophotography for maybe a year, some change. So I figured,
Yeah, we got a lot of astrophotography people. There's even a Discord group. I don't know if you've been acquainted with that yet. There's a special Discord group that HAL has. If you go on the website, there's information there. And so you'll find all of your peers who are into that money expensive hobby, and they will be glad to give you tips and suck you deeper into that black hole that we call astrophotography. So that's great. Welcome, Mom.
Thank you.
Appreciate it. Is there anybody online who is new? See a lot of familiar faces there. I don't see anybody new.
Hey, Jim?
So,
You
Yes,
might
sir.
want to announce that the reason it's probably a smaller crowd than normal is because this is the first day in over 20 years that the meeting date changed and not everybody got the word.
Yep, we are. Going to come up on that right now, I think.
Never mind.
Announcements. So as Phil just pointed out, we are now second Thursday of the month.
Jim,
Yes,
do you think you're sharing slides? We're not seeing anything online except the camera.
all righty, then you're right. Thank you, Wayne. Let's give that a try.
no better.
See if I can get this thing out of the way.
Okay, I'm seeing slides now.
Very good. All right. So basically, again, we were for years, what, 2 decades, 3 decades?
Since
2
we
decades.
started.
The third Thursday. So this is new. This is the second Thursday. So you'll have to mark up your calendars and change it to the second Thursday. Also a change of venue. We are no longer in the auditorium. We are in the classroom. So if you go into the auditorium, you will be participating in the Bird Club. We would like you here participating with the Astronomy Club. So if you did make this one and you're going to come next time, please keep those 2 things in mind. Our next meeting then is going to be the 9th of October and then the 13th and so on. All right, so schedule of events. I will apologize. Victor gave this to me the other night and I have been a cat on a hot tin roof at work and everything, have not had a chance to look at this. So the Star Party event that was held at the end of August at the Nature Conservancy, I did hear Victor say that that was very successful. Apparently about 10 scopes and over 100 people. And it's good. It's like cross-pollination, you know. We had a couple birders drop by and interested in astronomy, and we had people there at the Nature Conservancy interested in us as well. So it was good exposure. We have had impromptus. The weather has given us a little bit of a break after this terrible rainy, cloudy, hot summer. So there were impromptus that went well on the 11th, the 22nd, and the 29th. And as a reminder, if you want to be a key holder and start to do impromptus to be able to call them, you have to reach out to a HAL board member and discuss the process. We have additional keys. You would just have to have some training. The next public star party is coming up this Saturday, and miracle of miracles, I think the weather actually is looking halfway decent. So if you could come out and help support HAL, bring your scope out and show the public some of the interesting things. This is one of, I think, 1 or maybe 2 public star parties that we hold when the moon is not out in the sky. Normally we do it at a first quarter moon. This one is specifically geared to be able to give people more of a chance to see some of the clusters and the deep sky stuff. So if you are able to help us come out and show the heavens off, that would be awesome. September the 20th, there is the Astronomy Festival on the Mall. There is information in, I think, the website, and especially Victor is leading this up. He went last year along with Crystal. I know Victor said he had a line at his telescope well up until 11 o'clock at night. So there was huge interest from the public. And again, it was a great networking sort of event. So if you can participate with that particular outreach opportunity, please let Victor know and get in touch with him. And then finally, Crystal is hosting the Solar Science and Engineering Celebration at Glenelg on the 18th of October. And you can reach out to Crystal for more information on that. So here is the flyer for the festival on the Mall. Again, Saturday the 20th, coming up shortly. And, you know, from what I understand, it was a great event last year. It was very hot and humid last year. Hopefully the weather is going to stay through this little break that we've had. And then a little more information about Crystal's event. The Howard Astronomical League is a participating organization in this. It's free and open to the public. There are going to be several solar viewing stations that are going to be around the campus. And so Crystal's inviting everyone to celebrate STEM with the engineering challenges and demonstrations for K through 12. Crystal, you're online. Would you like to come off mute and have anything to say about this particular event?
Yeah, sure. So pretty much all those points, it really is just to really get families and kids excited for science and to, sprinkle in a little bit of astronomy as well. So the focus is that if the weather's beautiful and we have a chance to share views of the sun, we can do so safely and also have an opportunity to educate the public about, things like proper and safe observing of the sun, but also have lots of hands-on demonstrations. Especially for astronomy, we have a meteorite table. We have stuff like solar ovens where kids can like kind of melt the chocolate bar and kind of understand how solar radiation works. But overall, the goal is just to have fun and get the community out to enjoy the nice weather and some STEM.
Awesome. Yeah, I hope you have a great event.
Thank you.
So stick around because I think you're still up because we need you to talk about the book of the month.
Yes. So, this past June, I actually had an opportunity to go on a trip. And for those of you not familiar, in London, there is a historic Royal Observatory in Greenwich. And I got to see it for myself. And that was a bucket list item for me. And so this was a part of a STEM trip, actually. So I got to do this along with a couple students. So this was my souvenir book that I brought back to the US. So it is, of course, The Sun by Brendon Owens. It is a fairly short book, but it is a part of a series that is it covers things like the sun, the moon, stars. The goal is just to make some very common topics accessible to a wide audience. It is a fairly short book, kind of topping out with the glossary around about 117 or so pages, but it is a great coffee table book for going over some key aspects of why do we look at the sun? Why do we study the sun? What are some of those unanswered questions? And to kind of give anyone who doesn't have a background in astronomy kind of a little teaser into why the sun is so interesting and why we've studied it for so long. So, highly recommend as a fantastic beginner-friendly book. I also highly recommend checking out the Royal Observatory if you don't have it on your bucket list. It is a very neat place. They have a planetarium as well, and a lot of rich history to it.
Yeah, definitely. Very good. All right. Thank you so much.
You're welcome.
All right. So now we have a couple small talks here this evening. And the first up is Rich Russin. And I'm going to read his intro here. Rich and his wife, Millie, moved from High Springs, Florida to Severn in our neck of the woods in November of 2024 to be closer to family. He became members of HAL this past January. And his primary interest in our club are outreach opportunities and education. So as a former, well, I don't know if he's still there or not, but as a former member of the Alachua Astronomy Club, there's darn Indian names, Alachua Astronomy Club based in Gainesville, Florida. And over that time, he's held positions of club vice president, president, board member, ATM coordinator. And ATM, in case you don't know, is amateur telescope maker, a somewhat dying art, it seems like, that I think HAL is interested in trying to revive a little bit. Programs coordinator and a 3-time speaker of the month. His latest adventure has been the creation and management of the Far Out Journal Club, and I've seen him post on our listserv opportunities for us to join in that particular Zoom meeting. This was a spinoff from the Far Out Space quiz that he produced for the annual holiday party in December. So their favorite outreach happens to be the annual Grand Canyon Star Party. And that is what Rich is going to talk about this evening. So let me see if I can bring this up, and we want to make sure. All right, let's get this out of the way. And it looks like I've got the pointer.
Very good.
All right, Rich.
Yeah, I guess so. Oh, good. Everything's.
Options, come on. All right, do you want to drive?
Yes, I will. It'd be a little easier.
Absolutely.
The way you can relax and enjoy the talk. I've got everything.
So, do you want the camera pointed towards the speaker?
Well, I think,
Yeah, I guess so.
1 second before we start. Guys online, are you seeing the slide deck from Rich?
No, we're still
No.
seeing your slide deck. Yeah, I think you need, Jim, I think you need to stop sharing and Rich needs to start.
Well, it's actually this year's share.
Better?
Yes, now we're seeing it.
Okay. All righty. Well, to get this going, first of all, this was not a date and switch. It was supposed to be me and my wife. Unfortunately, last month we had to cancel due to COVID, and this month she got the bug in a week from our grandson. So it's just going to be me going solo tonight, but I think you'll still be just good. Looking for the down arrows. Here we go. All right. Yeah, I want to talk about the Grand Canyon Star Party. It's something we try to do at least every year and minimum every other year. It just happened again this last June. Okay, why is it not going down? There we go. This year, the Southern Star Party was held from June 21st to 28th. And it actually, North Rim was held at the same time. I'll talk more about that later. This was the 35th year of the Grand Canyon Star Party. Hard to believe that time's flown. And it's actually a collaboration of a lot of groups because it's really big. The National Park Service, Tucson Amateur Astronomy, and the Grand Canyon Conservancy worked in the South Rim. And then it changed it to Saguaro Astronomy Club is the club sponsor for the North Rim. There we go. This is a little bit different than a lot of star parties that members attend, in that it's really just all about public outreach, education, and just exposing people to the sky who have never seen a dark sky before. The Grand Canyon is an international dark sky site, which makes it particularly wonderful for that purpose. And this year's event is generally recognized as the best one to date in terms not just in the amount of volunteers, but the number of attendees and the enthusiasm and all the things that went into it.
Give you an idea of what's about each night. There's like setup and prep from about 5 to 7. And it's always, it starts on Saturday and it ends the following Saturday. 7 p.m. there'll be a general update where you'll get word of anything that's going on that you might need to know that night. So their big thing is cold popsicles, and there's a guy there that can do a really bad joke, always astronomy related. Um, from 8 to 9, we have our guest speakers. And then from 9 to 11, we do the public stargazing and we do constellation tours. And it's really impressive. I'll talk about that in a moment. Once the public part is over, then you can do your own thing if you brought equipment and you want to image or do things on your own. There's also, I mentioned earlier, the speakers. They had a full slate this year and they were excellent. I'm hoping that will go there. The one that we attended was by Dean Regis, and he will actually be on my Far Out Journal Club in the December edition, along with James Albury, and they're going to do kind of a dueling co-interview with each other. And so if you get a chance to see that, I'll be posting information on it. I'm not going to go through all these. I just wanted to say that there was really quite an impressive slate of speakers throughout the week. There's also social events that are held. And as you can see up there, there's a pizza party on Sunday, the IMAX and lunch in Tusayan. Tusayan is the town just south of the Grand Canyon. It's like Tusayan and then the entrance to the park. But they do have an IMAX, hotels, places to go eat. And then you got the Rancheros lunch on Thursday, and then finally Saturday, the catered lunch. So there are some formal scheduled activities. This year's event, we had great attendance, individual visitors, 6,777 at night, 9,616. And the number of contacts, this is eyepiece, eye to eyepiece, with 117,332. I pondered why the daytime was so high relative. And then I remembered at night, you only got 2.5 hours to go through that. Whereas for the daytime solar viewing, we were set up all throughout the day. So it generated kind of a false comparison there. As far as the volunteers go, there were 162 of them were required to pull this off. 4,103 hours. On any given night, we had about 77 scopes set up on the rim. It was really quite enjoyable. I can remember going back 15, 20 years ago, and we were happy to get 30. So it's been a big change. Just a few special notes. Astronomy magazine called the party the largest star party in the country. As I said, we had a record number of astronomers and telescopes. There were a number of changes that were done to improve safety, including the next line about this star guide positions for the volunteers, where there were people just to help people figure out where they were, what was going on. One of the things they did do, I don't know if it's going to show up on the camera or not, but they did require this year that you start wearing some sort of a red light device or just something as you were moving around. Unfortunately, about a year ago, one of the other sparks, another party, a ranger fell, hit his head, and died from it. And so they made this a requirement. Now, as the week went on, we were seeing less and less people actually wearing them because as you walked up to somebody, you blinded them. And so people were starting to put them either around their waist or lower in the pocket. But basically, it was a requirement starting this year. And then finally, the interesting thing is Ranger Raider Lane is like the head of the cultural aspect of the Grand Canyon Park, and incredible person, and so happy to know him. But they named an asteroid after him this year, 3280 Raider Lane. He's done an incredible amount for bridging the gap, not just between the park and the communities, but also with the Native Americans and dark sky initiatives. Now here's where I'd like to show you a little bit about how this is done. Over here, this is where the Grand Canyon is in this area. I'm hoping they can see it online. And what happens is you tend to come in from the south here on 64. And this is the main visitor center here, which I'll show you in detail in a moment. If you're staying in the park, we stay at Yavapai. You just go on down here, you can check in, and most of the rooms are either this area or this area. And then this is the marketplace center. It's there's some restaurants there, a nice fully stocked store, a good size one. And kind of unusual, they don't rake you over the coals with price increases just because they're pretty reasonable. Now, this is a blow up of the main area where we hold the star party. Over here to the right and upper corner, this is the canyon. That's why it's dark. It's dropping off there. The actual party is set up originally in this area right here. It's actually this, and this are all actually tour bus parking. That's why you see such large spaces. But we take over for the night, for the whole week, and we set up here. Now, as it's grown and we doubled in size with the number of scopes every night, this little crossover brings you to the second area, and we pretty much filled that now. And then the third area just tends to be where everybody that's here parks until they leave. So you can see it's just a short walk, maybe 50, 75 feet to the rim of the canyon. So it's really cool if you take a break, just walk over, catch the sunset, and come on back. Now, over here, in this area here, this is like the Grand Canyon Conservancy store. There's actually a little stage with a screen here, and they set up, this is where the talks are held every night. And then what happens is at 9 o'clock when the talk's over, everybody filters through here, up the parking lot, and then out over here to where all the scopes are set up. And again, this year they had people who were assigned to help guide people because you're going, it's pretty dark out there. And it's nice to have somebody kind of show you the way. Now, Millie and I did solar observing this year. Normally, I either try to get a scope or borrow it, or I had a friend who unfortunately had to cancel last minute. So what we did, I brought my little 60 millimeter teleview refractor, a little portable AZGTI mount, and set it up. And as you can see, there's the filter on it and all. And just in 3 sessions, we had over 400 eye-to-eyepiece contacts. And it was really, really enjoyable. Number of people who just couldn't believe what a sunspot looks like or something that basic. Same thing happens at night almost every year when you're with the scopes. They time it so that the Milky Way starts to rise about 9:30. And inevitably, somebody will say, oh, too bad the clouds are moving in. They have never seen the Milky Way. And it's just a wonderful feeling to expose them to that for the first time. Some of the pictures from the party this year, that's Ranger Raider Lane. He's pretty tall, about 6'7". Really, really knows the stuff. You can see along the edge here, you got scopes all being set up. That was in the middle lot. And this picture I took from a couple years ago, you could see again the setup, the store, and then sky in the background. This one here, just some more scopes. When you start talking 70 or 80 scopes out there, you're going to see almost everything possible in the way of a scope. Excuse me. The pictures here, just a few more. I gather there's some people who do this for a living. They just go from one party to the next. Now, if you decide to attend the 36th annual party, it'll be next year from June 6th through 13th. And I highly recommend you plan early. A lot of times, like if you want to stay in the park, you start getting scarce on the rooms, and also the flights and all. So it's something you should think about early. But here's the thing. If you're going for the very first time, you may want to consider just going as a visitor for the first time rather than a volunteer. In that there's just so much going on, and you get the lay of the land and just enjoy it. Go around for yourself and see through all these different scopes. Do a couple of days, and then there's 1,000 things to do in that area. Whether you go down to Sedona, you can go out to a meteor crater. Just so many different things to do there, and I'll talk about that in a moment. But if you do decide to volunteer, you will have to figure out what to do about your equipment. Like I said, we improvised this year. I brought the smallest scope I could that would get past security and not be damaged. And it worked out just fine. So it's 6 of one, half dozen of the other. We had friends in my old club that would drive out there and they would bring their own equipment. We're going to fly every time. That just way 24-hour drive. But you can fly into Phoenix, which is the way that we go, or you can go to Flagstaff down there, now accepting flights. We like Phoenix because it's not that bad of a drive to get up there. It's about 2.5, 3 hours. And then we stop at Sedona on the way back, sometimes in Phoenix itself. So where to stay? There's Tucson, which I mentioned is right at the entrance of the South Rim. I recommend just staying inside the park. From where we stay at Yavapai to the observing area, you can almost walk there. I wouldn't recommend it, but you could. There's lots of lodging available. And if you like to camp, they do have campsites that are generally free for people who are doing the outreach, but it's a limited number of sites. Okay, really quickly about the North Rim. This year, the Dragon Bravo wildfire has closed the North Rim for the foreseeable future. It started less than a week after the party this year, and they believe it was caused by a lightning strike. I was supposed to do this last month, and as of the 10th, it was only 44% contained. As of a week ago, it was 80%. 145,000 acres have been burned, and I just don't see any of the Star Party, Grand Canyon Star Parties being held there for a long time, and I'll show you why. Here's a couple pictures showing the gravity of the situation. The fire is really, really rough on it. You see the rim starts right here. That thing was burning right up to the rim. And it just really bad. This really hit the rangers, the staff, giving everybody really hard up there. This is what's left of the visitor center on the North Rim. Just not much left of it. Nobody really knows what the plans are. It's fire still burning, things are going on. So, I just thought I'd mention it. I guess it's fortunate we got one last party in before this happened. So I'm going to move to a more positive note here. This picture I took about 2023, and you can see here people are all set up in that middle parking lot. This is where everybody would come in from the lectures, and they go over, come in this side, and then start filtering in. While you're there, a lot of things you could do if you just go as a visitor. These are some of my favorite pictures I took a couple of years. Just amazing to see the canyon. I highly recommend you pick one day and just go to Flagstaff and Lowell. Flagstaff is a dark sky city. It's just so incredible to be up there at Lowell, look down at this big city, and it's barely lit. But if you're out in the city, it's lit well. It's just really amazing what you can do when there's a little willpower. In fact, you see there, October 24, 2001, they're recognized as the world's first international dark sky city. This is the new entrance to the Lowell Discovery Center, just opened in November. This is the 24-inch Clark telescope. A friend of mine from my old club helped provide major funding to restore it about 5-6 years ago. And it's just a wonderful scope. we got to look through it this year for the first time. And it's really nice. Also there, this is part of the new Discovery Center. If you go with family, this is the kids section of the Discovery Center, and they have so many interactive displays and educational things there. This is the GODO, the GeoVale observation deck and observatory, and they have a series of 7 scopes to die for that you can go there at night, look through. Really enjoyable. This building here, rather than like a thing opening, whatever, it just goes back on a track, and the scopes never actually move. They're there always. And then at the end of the night, the building moves forward and closes in. And finally, just bring a darn camera, and it just do some night sky photography, just some incredible opportunities to work on that part of your hobbies as well. So anyway, maybe I'll see you there. And that's it.
With all the scopes set up and people staying in hotels, you know, everything else, do the scopes stay set up, or do they have to get reset up every night?
Do you set up the scopes each night?
No, it depends on how brave you are. Some people set them up like the ones that you saw there. Let me see if I can find that picture real quickly. Gotta go back a couple here. I'm getting it. One more. Yeah, like this one right here. This guy, he sets it up one time, and that's it for the whole week. There was a fellow I knew a few years back who had a long, what looks like an Amazon van, who put an I-beam rail in the ceiling, and he would lift his scope up. The rail would come out, he'd put it on the concrete, and that was it for the week. Other people do set up and take it down, but for the most part, we've never had a problem. The closest we've had to an issue is one year we got all set up, and right at dusk, an elk came walking through. And everybody had the image of the bull in the china shop, and how many scopes could he take out. And finally somebody came up with the idea of just shining their flashlights at it, and it irritated it. He just turned around and walked off. So anyway, it'd be up to you whether to leave it or not. I've not heard of a single theft, damage, or anything. The closest I can tell you is that sometimes wind can come up, and we have had Dobsonians blown over.
Any other questions? Anybody online?
Yep.
All right, Rich, thank you very much. That was a great presentation.
Great.
I am looking to see, is Matt Peters in the audience this evening? Matthew Peters. I don't see him.
He doesn't seem to be online.
John Nagy says he sees him.
No, I don't see whoever you were just looking for. I saw someone else I saw.
Okay. All right. Perhaps he could make it this evening, and I know we had trouble uploading his presentation stuff, so I think we'll go ahead and move along. If he joins us later, maybe we can circle back. And so that will bring us to, well, I'm not going to share the screen for this part here. So this is going to bring us to our featured speaker here this evening, Dr. Mehdi Benna, planetary scientist from NASA and Goddard Space Flight Center. Dr. Benna is a senior planetary scientist at NASA's GSFC and a research professor at UMBC. His expertise spans plasma physics, planetary magnetospheres, development of cutting-edge space instruments. We've Got one of them here, a sample of it tonight, a mock-up. It's a shame for you guys on Zoom that you're not seeing this. Maybe we'll have the camera so you can see it. If you followed missions like MAVEN, Lady, or the Mars Science Laboratory, you've already encountered the impact of some of his work. So Dr. Benna has led or contributed to more than a dozen space missions, including the Artemis III Lunar Environment Monitoring Station, which is the topic for our talk this evening. The SEAL experiment investigating lunar surface interactions, and the Mosaic spectrometer for the Geospace Dynamics constellation. His research has been published in over 100 peer-reviewed articles and presented at more than 200 international conferences. He's also the recipient of multiple NASA awards, including the Exceptional Achievement in Engineering Medal and several Group Achievement Awards for his contributions to Mars, Mercury, and lunar exploration. So Dr. Benna,
All right,
the floor is going to be yours. How do you want to
thank you. How do you want me to place myself?
So do you want to be demonstrating your PDF?
Yeah,
online?
let me sit in here if you don't mind, just kind of scrolling kind of running this slides through, and I'll be more on the side so I can show people as I speak.
All right, that's
Sorry, are you guys supposed to be sharing slides right now? People online can't see anything.
working on it.
Oh, sorry.
No worries.
Hey, Crystal, were you seeing both the camera and the slide simultaneously?
Yeah, so I can see the room camera and the slides, but we
Okay,
just
so
don't see
we'll
slides
move-
right this
right,
second.
We'll move the camera so you could see the demonstrations along with the slides.
Yeah, and for those of you on Zoom, if you don't have a decent image of the camera from the room, you may have to go change your view up in the corner.
Yeah, we see the slides now.
I mean, you got it?
Well, I don't know that you can share both.
Yes, they're seeing both. Yeah.
Hey, Mehdi, it's John. I was gonna surprise you and ask you a question about neutral gas ions or something like that.
Okay, great. So John is
They already outed me as being in the group.
all right. Awesome.
Congratulations.
Okay, you
thank
got
you.
it.
Okay, Bill, I got you.
And you have
There's slides for
slides
supposed
in
to
there.
be in here.
Yeah.
You know what?
TV lost the signal.
Don't pull that. Here, I got it. So we don't want to disconnect your computer, so.
I'll get the remote again.
You guys had problems on this side, not on yours, so.
Checking the noise, no signal.
The way it went back to talking about.
Let's go back to home. So. There is just the issue now.
Let's try this. Signal.
We don't want to reboot the computer. This is just a few weeks out. We're all sales control on delete.
Yep. All right, while you're doing that, let me start so I don't take too
Yeah.
much people's time. So thank you for hosting me tonight. I had to explain to my wife why I'm missing dinner tonight, and she approved. So we're all lucky. Yeah, she doesn't approve often, but tonight she approved. Thank you for the introduction. So I'm the principal investigator of one of the experiments that will be carried by the crew of Artemis III to the lunar surface. As some of you know, Artemis is the equivalent of Apollo It's the new program that it's designed to send crewed mission to the lunar surface for exploration. And it will start like Apollo. It'll start with missions progressively that went from an uncrewed vehicle to a crew that will go around the moon with Artemis II to a first landing with Artemis III. The Artemis III timeline, if you believe it, expect that we will be landing by late 2027. The Artemis II mission is about to launch in a few months, and so about a year and a half later, Artemis III will launch. And since we will be landing on the surface, one of the goal, other than to test the equipment and the vehicles and the suits, it's to deploy science instruments, like pretty much like Apollo did on every of the Apollo missions. For Artemis III, NASA selected 4 instruments that will be delivered to the South Pole. 3 are US instruments, and 1 is a contribution from the Japanese Space Agency, JAXA. And so I was one of the fortunate ones to get selected with my team. We were selected with an instrument called the Lunar Environment Monitoring Station, and that story of the instrument is a little bit peculiar. It came really out of a necessity. I am a planetary scientist. I specialize in building mass spectrometers and studying upper atmosphere of planets, rarefied atmospheres like the exosphere of the moon. And with the current level of technology we have, unfortunately, we very quickly realize when you build instruments that your instrument will only be, if you ever decide to deploy it on the surface of the moon, will only be able to operate for about 8 to 10 days. And the reason is currently in the NASA portfolio, all vehicles that go and land on the moon can only operate during the daytime on the surface, which the moon, as you know, spend about 30 days to rotate around itself, and so 15 days of day. If you land in the early morning, and you probably will last about 10 to 11 days by the end of the mission. Once the hardware and the lander and its hardware goes to the night side, temperature plummet very quickly. You go on the surface of the moon to about minus 200 Celsius very quickly, and you stay there for 15 days. So it's a big, giant, long freezer. And so the current state of the hardware, it's not designed to sustain such a cold time. And so facing that reality, I was a bit annoyed, and I said, all right, well, let's see if we can solve the problem. And I had was fortunate at the time. I had a small engineering team, and we kind of took a little stab at it, and we realized that actually one way to solve the problem is to not try to make an entire lander survive the lunar night, because it's going to take a lot of energy and for heaters and things of that sort. What if we build just a small little buoy, a little cocoon, that we equip it with everything we need? It's small, so the amount of energy it takes you to maintain things alive, it's proportional to mass and volume. And so the smaller you are, the easier you can stay warm, and the less energy you need to survive the night. And so we embarked on designing this, what they call the buoy for the moon. The idea is to build this very small, self-contained science in a suitcase, a science package in a small volume. And that little suitcase should have all what it takes to do science, but also all what it takes to relay that science down to Earth in a simple way. And We dubbed it the Lunar Environment Monitoring Station because we realized very quickly that, oh, actually, you can put whatever instrument you want on it. As long as you want to monitor the environment of the moon, whether it's the seismicity of the moon, the magnetic field around the moon, the exosphere of the moon, the nature of the solar wind as it interacts with the surface, anything that you want to observe for a long period of time that spans months or even years, you can place it in this basically in this little suitcase, and the suitcase will take care of it. We'll keep it warm. We'll keep it operating, and from time to time we'll link to that suitcase on the surface of the moon via ground station on Earth, and we'll download the data. And so it operates a little bit like a buoy in the ocean. Those rugged buoys, if you go on the Chesapeake Bay or the Atlantic Ocean, you'll see them scattered. NOAA have about 5,000 of them around the globe. And they operate pretty much the same way. They're rugged. You drop them out. They're pretty cheap to build, actually. You drop them out in the ocean. They're fairly rugged. They sustain themselves on their own. They have solar arrays, batteries. They generate their own energy and they store it. And they have simple instrument on board. And they take their data and they store the data and the satellites ping them once a month and just pull that data out. And so we said, let's build a buoy for the moon. And that buoy is what we call now LEMS. And so since this is going to be deployed by Artemis III, we call the first one LEMS A3 for Artemis III. The hope is that we will replicate this on future missions, and you will have multiple versions of these. So LEMS is led by UMBC. I'm a UMBC professor. It's been implemented by NASA Goddard a few miles away from here with a partnership from University of Arizona, Morehead State University, Washington University in St. Louis, and UMD, University of Maryland College of Boston. Next, you don't mind. So the first slide, I told you pretty much everything you want to know. The concept is to truly build a self-powered, self-managed, and self-communicating flight system, a little suitcase that can do science on it by its own continuously, day and night, and completely autonomous. You put it on the ground, you flick the switch on, and you walk away, and it will take care of itself for years. For the Artemis III, we pitched the science that's of the highest priority for Artemis, which is seismology. And we were selected to carry 2 seismometers built by University of Arizona. One is called the short period, one is called the broadband seismometer. Now we'll talk about those a little bit later. What you see here, I brought with me is a mock-up, a fairly high fidelity mock-up of what that LEMS looks like. As you can see, it has handle, so the crew can pick it up and walk with it. I'll show you how it works later. It's a giant toolbox. It weighs about 30 kilograms. So on the moon, it's going to be about 5 kilograms worth of weight, pretty light. And the seismometers are parked here, and the crew will deploy them once on the surface. But we'll get to that a little bit later. Next. All right, so why LEMS for Artemis III? We actually fill the gap in 2 areas for Artemis, and that's why NASA kind of decided to carry this payload. Number one is the longevity. The Artemis mission, the crew will be on the surface for about 5 to 6 days. And so if you want to do any type of science that require observation for weeks, months, and years, you need to something like LEMS. The second thing, it's really much easier to deploy than what the Apollo crew had to deal with. In the Apollo era, NASA commissioned a series of instruments. Each instrument has its need in power, need in thermal conditioning, need in telecommunication to relay the data. And so NASA built this massive central station that has all the smarts and the computers to gather the data from these instruments and command them. It put in a radioisotopic generator, basically a plutonium battery, or power source on the surface to provide power day and night. And so instruments at night, so they don't freeze, they give them the this basically infinite basically source of supply of energy, and so they brute force their way to survive the night. But it consumed deploying this type of configuration of instruments called LSAP for Apollo consumed a lot of time from the crew, because there's a lot of cables running around, hooking up multiple elements. And so with LEMS, everything is in one package. The station is in here, the power source is in here, the instruments are in here, the telecom system, everything is in the same suitcase. So it's much easier to deploy. The crew walks on the surface, put it down, align it, flick the switches, walk away. Next. So why seismology? We want to basically monitor the seismic activity of the moon for really 3 reasons. Number one, we want to understand what type of seismicity does the moon have in the South Pole. The Apollo missions, almost each one of them deployed a seismometer at the landing location. But if you look at where the Apollo mission landed, they're all near equatorial. And so we have really blind spots on the pole. We don't know what's the seismicity of the moon in the North Pole. So we're going to put this instrument just to listen and see what's out there in terms of seismicity. Then with the seismic event that we'll be measuring, we would be able to characterize the moon's internal structure. We can use those the seismic events almost like an X-ray. They travel through, they're generated somewhere, either deep in the mantle or the core or right at the crust, and they have to travel through the lunar material to reach us. And so the seismic waves will be deformed, will be tainted by the constituents of the crust, the mantle, and the core as they travel to us. And so by reverse engineering that signal, we can actually tell what is the internal structure of the moon. The third objective is more of an exploration objective. As you know, the Artemis program is set to really establish long-term presence of astronauts on the surface of the moon. We'll kind of do that by building potentially habitats, having astronauts stay there for weeks, possibly even months. And so if you are planning to build a house somewhere, you want to know what are the hazards. Is that a floodable area? Is that a seismic area? And so here's the same thing. We don't worry about flood on the moon, but we worry about seismic activity. The moon still have quite a bit of seismicity, and that seismicity is very patchy. And so we have to really map the entire South Pole if we ever want to settle there, to decide where we are going to build all the infrastructure. And so by placing LEMS early on in the Artemis program, we would be able to collect that long-term data that hopefully in 2, 3, 4 years, we will be able to pinpoint areas of hazards and areas of low seismic activity where we can build structure. Next. I'm going to very quick talk about the type of seismicity we can detect. The seismicity on the moon is quite different from seismicity on Earth. The seismicity on Earth is mostly due to tectonic plates moving around, crushing in each other. On the moon, you don't have really tectonic, the same tectonic phenomenon you see on Earth. But because the lunar interior is still we think is molten to semi-molten, things are still moving a little bit. And so the Apollo mission detected clusters of deep moonquakes. These deep moonquakes are deep in the mantle, almost some of them at the edge of the core. They also detected a lot of shallow moonquakes. These are due to scarps features on the surface that under stresses they release their energy, and they create these shallow moonquakes. As you know, the moon librates as it moves, and because of differential gravity pull between the sun and Earth, that crust get a little squeezed like an orange, and from time to time it cracks, and so that makes the shallow moonquakes. We get a lot of seismicity due to meteoroid impacts. So we see when we see meteor showers at Earth, that same meteor shower is impacting the moon, and so you get impacts from micron-sized particle to meter-sized particle on a regular basis, and those create a seismic wave that also propagate on the surface. We get a lot of thermal moonquakes, and these thermal moonquakes due to the gradient of temperature that the moon experiences. As I said earlier, the surface of the moon at night is at minus 200 degrees Celsius, and it shoots up to above zero very quickly at sunrise. And so in the sunrise and the sunset boundaries, you have terrain that in one side is freezing and one side is getting really hot, and that create a lot of thermal shifting and create those thermal moonquakes. And finally, if you have exploration going on with astronauts walking around, you're gonna hear a lot of noise. You're gonna see cracking from vehicles running around. You're gonna see the astronaut dancing on the surface. You're gonna see all the activity that it takes to deploy all the infrastructure and the instruments, and that is by itself carry a useful signal for science. And so what we set to do with these two seismometers we carry is to measure the timing of these events. When do they occur? When do they occur in absolute time? When do they occur in relationship with each other? When do they occur in relationship of the lunar, the moon, it's an orbit, and the sun, etc. So we can pinpoint sources. We try to record the amplitude because that tells us how far the event location is, and we try to get bearing also because I'll talk a little bit later. We have 3-dimensional seismometers. We can determine bearing of where the signal is coming from, so we can geolocate every seismic event around the entire lunar globe. Next.
Quick question.
Yes.
So in a lunar eclipse, would that be more pronounced in terms of the thermal shock?
Yes.
Okay.
Yes, you will see. So Apollo detected during eclipses, detected thermal quakes, not from the surface, but from the infrastructures, because those seismometers were not far from the LEMS, from the rover left behind, and you can see them creaking and cracking as the shadow moves and the temperature plummets, and then they heat up again. It's all, I don't recall ever seeing data from thermal transient of the surface through an eclipse, but for the infrastructure, we see a lot of it.
I have a question.
Yes, please.
So, in envisioning these quakes, so when you think about a quake here on Earth, the ones that make the news, those are a big shape.
Yeah.
So are these lunar quakes have enough force or whatever that if you were just standing there, you would feel them, or are they just really size?
They do. So you have to scale everything on the moon because we compare the earthquakes in terms of Gs, right? In terms of the Earth gravity. And so if you take that same scale and go to the moon, which is 1/6 of the gravity, you can get magnitude 5, magnitude 6 earthquake on the same scale, but relative to the lunar G. So a crew that is sitting on the surface will feel the same acceleration from the ground as you will get an equivalent earthquake of the same magnitude of the Earth. So they can be quite violent.
So another question. So is it cause? So I love observing the moon from here, right?
Yeah.
So, because my spaceship is still in shop.
Yeah.
And you can laugh. Okay, thank you. So anyways, is there could you see any visibly see any of the change in the outer structure of the moon?
No, not really. So you're not going to see it from Earth. I mean, we're talking about displacement of few millimeters, few centimeters. So what you feel in an earthquake, even on Earth, is the acceleration. Is when things shake you back and forth. There's acceleration, even if ultimately at the end the ground goes back to its position. Everything is in the same place. And so when you have a seismic wave traveling through, it does not necessarily result in dislocation and faults and things like that. We see in a lot of the mapping of the moon, a lot of scarps, a lot of faults that clearly opened up due to seismic events. But you cannot really detect that from the ground, and even with current assets on orbit, we never saw it happening real time. But the Apollo, all the Apollo seismometers over about 7 years detected about 15,000 seismic events around the globe, and some of them are very, 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 very important. That it makes basically the crust rings for weeks after that event. And so there, it's seismically fairly active body. So what's interesting about Artemis is we're going to the lunar South Pole. So the lunar South Pole, obviously, for as most people recognize, it's really famous for the volatile deposit, the ice deposit that we think there exist in these permanently shadow craters. There are craters on the South Pole and North Pole where the sun never gets to. And so all those volatile gases that may have been delivered to the moon billions of years ago have accumulated in those cold traps. And so the Artemis setting site on the south pole of the moon, mostly because there are reservoirs of volatiles. That means we can generate fuel in there. Possibly we can make water. We can make a lot of things. And so from a practical point of view, there are a lot of usable resources there. But from a science point of view, the fact that there are cold traps means the volatiles that basically contributed to creating Earth, creating our atmospheres in our early history, and possibly led to life. The traces of those gases are still trapped in there. So the south pole of the moon is almost like a freezer that hold the building bricks of the volatiles that made Earth habitable. And so we want to go there and get a sample from there. For seismology, as I said, it's being in the South Pole is truly getting to an unexplored area of the moon. We really don't know much of the seismicity there, and so putting a station in the South Pole is going to fill a big gap in knowledge that we had since Apollo. Next. So I talked about this in the beginning. I'm not going to spend too much time. LEMS is designed like a buoy. I had to start imagining what it should do as a system. I said to my team, it has to be self-sufficient. We need to be able to survive on the moon, operate without another vehicle, somebody pumping fuel in our reservoir or providing us power or anything. We need to be self-sufficient from a power point of view, also thermally. We cannot rely on another vehicle to give us, or another lander to give us heat, or to give us or cool us down during the day. Long-term sustainability. The goal is to do science for a long period of time. There are things we want to observe that takes years for the sciences and the variation that happens over years. So we need to be able to sustain ourselves. And so to sustain yourself with a minimum amount of power, we designed what we call a hibernation awake scheme. The station itself, it's asleep 99.8% of its life. And by sleep, it turns off everything but the science instruments. It leaves the science instrument, taking the science, but we turn off the comm system, we turn off the computer, we turn off the power system, we turn off everything you can imagine. We have a switch on it, we turn it off. And that's allow us to conserve power, and that's allow us to use very little energy to sustain ourselves. But from time to time, we wake up once a day for 20 minutes. The entire station wakes up. It wakes up its power system, its comm system. It wakes up its avionics and its computer. So we can, when the station wakes up, it it goes and fetch the data from the science instrument, do some crunching, compression. It checks that everything is okay, the station is still alive. If there is a heater, if the station is getting too hot, we turn off a heater. If it's getting too cold, we do housekeeping. And then after 20 minutes, it goes back to sleep. And the balance between that period of hibernation where we're almost living in a vegetative state, and the period when the station is awake, where it consumes a lot of power, that's what allows us to sustain ourselves continuously. We're always power positive, and we can survive the night and operate continuously. The operational autonomy, we wanted to make sure that the station just operates on its own. Typical spacecraft requires that you check with them quite often and load new scripts and make a trajectory correction maneuver and things of that sort. You have to be maintained. You cannot leave a spacecraft on its own for a long time. We wanted LEMS to just carry on as long as nobody talks to it. It's going to keep taking science, almost like a buoy in the ocean. So we can let the station take science for 2, 3, 4, 5, 6 months and never contact it. But when we want to contact it, it will be there, and we will be able to download that data from six months ago. Next. And so the results of all that, when you put it together, you get to this little box here. And so, as I said, it's the size of a toolbox. It's going to be mounted almost like this, at this height, with this configuration, in the human landing system, which is built by SpaceX. Is the gigantic Starship. And so we will be placing the LEMS in Starship before it goes to the moon. Starship will launch, will rendezvous with the crew that will be coming by themselves with another vehicle, with Orion capsule. They will meet in lunar orbit. They will just transition to the human landing system, and the entire SpaceX human landing system will land. Once on the surface, the crew will be able to remove these lunch locks in the back and pick up LEMS and just get out of the hatch and walk on the surface. LEMS has everything you need in a typical spacecraft, other than propulsion, because we're on the surface. We don't need to fly, and so we don't need propulsion at all. But other than that, it has a battery inside. It has an avionics system, which is a computer that manages all its operations. It has a power system. It has a solar array to provide power during daytime, and the battery will store the power and provide it at night. We have 4 antennas in the front. We have 2 medium gain antennas and 2 low gain antennas. We use the low gain antennas just to trickle down data, but they're fairly robust. They can pick up Earth pretty much at any direction. The medium gain antenna is our Wi-Fi link. It's a high speed, more directional, and that's our main way to get our science data. On the side, we have a little carrier box. Inside the carrier box, there are 2 seismometers. There is one, this long tube called the SP, and one that is the size of a shoebox called the BB. And those are 2 optical interferometry seismometers. In the Apollo era, they had really mechanical seismometers. A giant mass held by a spring with a little mechanical thingy that when the moon surface shakes, the entire thing shakes, and there is a little potentiometer that records the motion, digitize it, and send it to us. We came a long way since then, and so now we still have a mass spring system inside, but the motion is recorded by a laser interferometer. So we measure the displacement of the mass relative to its rest position with a nanometer precision. So we can detect acceleration in the nanometer second squared type resolution. To explain sometime how sensitive LEMS is, if you take 1 kilogram meteoroid that we're on the South Pole, that impacts the North Pole, we will hear it. That's across 3,000 kilometer body. And so it's very, very, very sensitive. The reason we have two is because, and they have separate names, one is called short period, one is called broadband. It's because they slightly detect seismic events over slightly different frequency band. They overlap, so they are redundant. So if you lose one, you can do quite I would say 80% of the science with the other one. But instead of just making two copies of the same seismometer, we decided that they would be slightly different, so we can get a broader science return. It has here you see the sun sensor. The station need to know when it's day, when it's night, so it can calibrate all its operations. So we give it two sun sensors, one on the left, one on the right. And since we are trying to communicate with Earth, and Earth is a fairly small object in the sky on the moon, we need to align this quite precisely. And so we gave the astronaut a very sophisticated method to do it, which is a bubble leveler and a sundial. And it's actually a funny story because this is how Apollo lined up all the instruments on the moon. They had a bubble leveler that gives you horizontal within a few degrees, and a sundial. And if you know what time you are on the moon, you can guess what the shadow should look like, and that tells you your orientation, the azimuth. And so when we started LEMS, one of my engineers came so excited and gave me this little microchip. IMU is an inertial mass unit, and basically it's a microchip that can give you attitude. So for small sats and CubeSats, and so he said, this is how we're gonna align it. Gonna put a bunch of LEDs for the crew to see, and you can move it, and the LEDs gonna tell you green or red and yellow and things like that. And I went to Home Depot and I got him a bubble leveler, and that was the end of the story. Next. So to get here, a lot of people don't realize that really you don't develop an instrument or deploy hardware in space in general, like just right away. You have to go through what we call at NASA the technology readiness. The technology maturation, which takes you from a technology readiness level of 1, which is a sketch on a paper napkin, to the technology readiness level of 6, which is I am ready to go to space and I can sustain the environment and I can operate as required. And so we were fortunate, and before we got on Artemis for a few years before that, we got enough funding to build a prototype of this. And so we built one in the 1999 to 2023, 2022, and then we tested it, and we went through the rigor of testing to the space requirement, which is vibrating the instrument to simulate the launch loads that an instrument will see at launch. We put it in a vacuum chamber to simulate the environment of space with the heat and the cold, and we demonstrated that if you put this thing on the moon, it will operate as intended. And so that was the start of the flight system that you see here. Next. No, you went the wrong direction. There you go. So the seismometer themselves, as I said, they're really, really little nifty little pieces of hardware. University of Arizona actually teamed up with a company called Silicon Audio that makes speakers, audio speakers, and audio speakers vibrate. They're so and you have a coil that generate the basically turn a electrical wave into just a mechanical motion, and it vibrates, and they're very, very sensitive. So what they did is they reversed the speaker. It's a speaker that was reversed, so vibration is coupled to a very precise coil that gives you an electrical signal. And so you can see actually the coils here, and so to detect the motion, they put a laser interferometer, which is a tiny little board here that has a little laser and mirrors, and by looking at the laser interferometry patterns, you can tell how the membrane basically it's moving, and so The plot on the right, it's basically giving you in a scale of sensitivity, what we call the sensor self noise. We'll disregard the units, but the lower you are on that log scale, the more sensitive you are, and the higher you are, it's the less sensitive. Also, the lower you are, the less energetic the seismic event you're trying to measure. The higher you are is the more active, the more intense seismic events. And since the seismic event is a wave, we measure it in the frequency domain. And so what you see the bubble in blue, those are the type of seismicity that we're after. We're active sources, high frequency seismic events, surface impacts, tidally induced deep moonquake. So that all occupy this area. And the red and the blue curves are our two seismometer envelopes. They can detect anything above that envelope. And you can see how we hug nicely all those blue bubbles, which means that we can detect pretty much all these type of seismic events. Next. All right, so the reason they also, these seismometer have slightly different shapes is because we are planning to deploy them differently. The skinny one, the SP sound, which is a tube about 4 centimeter, 2 inches or 1¾ inches in diameter, we made it on purpose to be exactly the diameter of the core, the boring tool that the crew will have. So Apollo, when all the Apollo missions, they returned core samples from the ground. And these core samples were as deep as 70 centimeters in the ground. And to do that they had these coring tool. They're hollow tubes that they insert in the ground, and they hammer them if they have to. And then they pull the core sample, they put the plugs, and they bring it back to Earth. When they do that, they leave a hole. And here's a picture from Apollo 15. You can see on the left an astronauts basically pushing the tube in the ground, and they just extracted the sample and they gave that hole. And so the lunar soil is an amazing thing. It actually have an incredible amount of cohesion. You can pull a hole at 70 centimeter deep, and that hole will stay intact. It will not collapse. On Earth, it's very hard to do because we have a higher gravity, and the Earth soil is usually very weathered. It's not jagged or there is no sharp angle, so it doesn't stick together, doesn't have much high cohesion. On the moon, there is lower gravity, so there's less force to collapse a hole, and the lunar soil is very, very it's not very weathered, so it's very cohesive. It's when you take a piece of dust and look at it under a microscope, it looks like a snowflake. It's very has sharp angles, and so all those angles intermingle, and it keeps the column of soil all intact. So the plan is to, after they do that, they're gonna take our seismometer, they're gonna fit it to an extension tool, and they're gonna drop it in the hole, and we size it to be exactly the size of the hole. Next. The second one is called the BB. It's the big one, and so there are all the sensors are in the housing of a side of a shoe. And go ahead, next. And the plan is to dig a trench and put it in a trench. This is a trench was done by Apollo 17 by Jack Smith. Trenching in the moon is a complicated on the lunar surface is quite complicated operation because the suits are bulky, and the crew the astronauts have very little visibility with their helmet, but it was feasible on Apollo, and so we know roughly what type of trench the astronauts can do, and so we sized our BB to be roughly the size of a feasible trench, and so the plan is to trench about 10 inches deep and bury the BB in there and just put soil on top of it. So the SP and the BB will be about I would say 3 to 10 feet away from the station, and they will be connected to the station via ribbon cables. And so the ribbon cables, that's what provide them power and get the data back. Next. And so this is what things would look like on the surface. So you have the human landing system on the moon. The crew will walk about 100 meters away and will put us down and will extract the BB and the SB that will trench them on the side, and the sun will be on the opposite side. Next. And so we've been actually doing that for the last year. There is a facility in Florida that belongs to University of Central Florida, where you have about a 30 feet by 30 feet sandbox, and that sandbox is made of a lunar soil analog, about 3 feet deep, and somebody comes every morning and fluff it, spend 2 hours fluffing the lunar soil. And so we go in there and they can recreate the lunar lighting. You can see how the lighting in the South Pole is very, very grazing angle, so you have long shadows. And that allowed us to practice and demonstrate that we can deploy it. We were about a month ago there again with a crew from Johnson Space Center, which we were kind of training. We're training the trainers. We don't train the astronauts directly, but we train the trainers that train the astronauts. And so we are in that phase where we are training the crew and trying to see how that we can optimize the deployment. What are the contingencies? You know, the crew is by themselves there. So if they pull a cable and something snap off, what do they do? So we have to think through all these contingencies. Then that's what we're doing right now. Next. These are more pictures of our deployments. We were able to extract a hole that looks strangely like the one on the moon. This is an example of our BB being deployed and somebody trenching there to deploy it. You can see here our sun bubbler, our sundial, and you can see the shadow of that little stick that tells us basically the orientation of the hardware on the surface, and you can adjust that. And so it's a lot of fun. It's truly when I have to tell my wife when I'm going there, I'm saying going to play in the sandbox, and it's truly I'm not lying. I'm playing in the sandbox for a week. So that was a lot of fun. Next. I'm gonna skip that. Next. And so the takeaway of this is that LEMS, it's for us is very, very historical. It's the first crew delivered lunar geophysical instrument since 1972, 50 years ago. It's going to deliver one of the high priority science for Artemis with the new technology, not only in the bus but in the instrument themselves. We expect the instruments and the station to last for many years, and it's going to be at the South Pole, which is one of the least characterized environment in the solar system. And so again, it's a culmination of many years of R&D, of a lot of sweat and tears from a lot of people across multiple institutions. And I think that's it. And if you go one slide more, that's the team. This is a picture from us during our critical design review. Flight hardware have to go through multiple, NASA put us through the rigor of multiple peer-reviewed events or milestones. And this one was the critical design review by which we are allowed to go ahead and build the hardware. And if you have any questions, please.
Oh, I don't know.
Oh, I'm sorry. Yeah. Oh, yep.
Go ahead.
Who's going to make the final determination on exactly where that thing goes?
A lot of people. It's going to be a big fight. They're going to put a lot of people in a room, going to lock the door and say, just put a dot on the map. And it's really complicated. I'm joking, but it's not that far off. There are a lot of aspects. Obviously, we want to send the crew to a place where they can land, regardless of the science. There is no science if we cannot touch the ground safely. And so crew safety goes first. Capability of the vehicle for landing will dictate where we're gonna land. So the people who design the vehicle, who know the crew's capability, will take the map of the moon, will take specific spots, and maybe there are right now 9 of them. There are 9 regions in the South Pole, each one about 100 kilometers by 100. and they will say, all right, you got a scientist, you got to pick something within these blocks. And then it goes to the scientist and the geologist, and we gonna have to, argue a bit and come to a consensus. But it's a combination of how easy it is to get there, how safe it is for the crew, how suitable it is for the instruments. Each instrument has its own requirements. In our case, we want to be able to communicate with Earth. So don't put me in a spot where there's a mountain in front of me, right? Because I cannot see the Earth. So we have to reduce all those possible sites to just a set of few, and those goes to the mission. They will kind of pick maybe 2 or 3 as prime and 2 or 3 as backup. And because these are all now linked to when you can launch, because depends when you launch, you may access one site, but you cannot access the other site. There's a lot of orbit trajectory that goes into it. And so we will not really know until we get there what exactly the site we gonna land. We're gonna be most likely carrying 2 or 3 possible sites until we get there. And then depending on how the mission goes, we'll end up on one of those. Then once we're on the ground, will be a frantic run into, all right, now we're here, we're really landed here, let's see what we can do. There will be a baseline plan. People would have run these scenarios before, but now it's going to be a reality. That lander could end up a kilometer from where you expect it to be. Many of the Apollo landers actually missed that exact hit spot, and they ended up a little bit off, and the scientists and the engineers had to very quickly work a plan with what they have.
So Dr. Benna, we have an online question. John, you want to ask your question?
Yeah, hi, Mehdi. Fascinating. This is fascinating. I love it even more than NGIMS. First question, I have a 2-part question. First one is about the capability. Would you expect during the annual, say, Geminids, Perseids, Leonids, would you expect to see just a rash of seismic activity for, I don't know, 24 hours or 36 hours, however long it takes the moon to pass through those meteor showers?
We should, but not for those you cited, because those are equatorial meteor streams. One of the things we don't know, even on Earth, we don't know the high latitude meteor streams. All the meteor streams, if you go to the website of the International Meteor Society and look at all the known annual meteor stream they get, they all end up almost at 60 degrees of latitude of the radiance. That means the shower seems to be coming from a cloud at that angle. We don't know of any meteor stream that is vertical, that is a 90 degrees, that's going to hit the ground straight down. And we don't know them, not because they don't exist. We don't know them because we just have no way to map those. To map high latitude meteor streams on Earth, it's, most meteor streams are faint, so they have to go through the atmosphere and you're not going to see them. And we don't have any other means to map them out. So if there are high latitude meteor streams, we will pick them up, and we'll pick them up exactly like you described them. We're going to see there is what we call the lunar hum. So there are small seismic events happening everywhere on the moon. If you are anywhere on the surface, you'll hear a hum. So it's what we call the moon hum. And that moon hum during meteor stream will increase. It's like you are in a train station with people talking all over. You cannot make up any single conversation, but it is there. And so that noise will increase as meteor stream passes by, and you can see them increasing for a few days and then dying down for a few days. But what we will pick up as distinct hits as anything within few centimeter size that can hit up to a few kilometers away, we can actually pick it up. We're very sensitive. If it's a kilogram mass meteoroid, we'll pick it up from the other side of the moon. So we expect the hum to increase as we go through meteor showers, if there are high latitude ones.
Amazing. My second question is more about the package, the LEMS. Are you in any discussions for future instruments that would replace the seismometer on, say, future moon landings?
Yeah. So the NASA, the way it chose to select its instruments, for Artemis is through competitive bid, through basically a proposal selection method. On Apollo, they actually hand selected the instruments. There were, at that time in the 60s, there were not many institutions that can build instruments anyway. And so NASA basically reached out directly to the institution that they knew had instruments of that type and just gave them money to do it. The landscape changed since 50 years later. There are many people that can build wonderful instruments with high capability science. So NASA just compete them. We competed on the Artemis III. We were one of the lucky that got selected. We are competing on Artemis IV also. So we're waiting. We should hear any day now of the result of the selection for the Artemis IV instruments. And we propose the LEMS A4 that does different science. My grandpa used to tell me never tell the same lie twice. And so you cannot pitch the same science twice and win it. So we build a complete different type of science where we'll have a mass spectrometer going after volatiles. We'll have a micrometeoroid detector on LEMS A4, and we'll still have the seismometers. But the goal here is to go about different science, and the hope is that we can get selected there. After that, we don't know. The hope is at some point NASA will see the merit of the station as a bus and possibly decide to just make it as a standard feature of all the Artemis missions. That is to be seen.
That's great. Thanks.
We had another question in the room.
I guess I was just recently listening to a presentation by a couple of folks from NASA and the Planetary Society. And I was surprised to find out the recent budget reconciliation, how devastating that was to both operational programs, but also planned programs, as well as access to contractors. So I'm curious, did that impact this program or programs that it depends on?
It does. So I'm going to speak on my little instruments, right? I don't have visibility to the entire Artemis program. You know, I'm a little tooth in the gear of the great machinery. But we are part of the same microcosm, right? We get NASA funding. We use engineers and contractors and scientists that operate with NASA, that are funded by NASA. So if the budget kind of goes up or goes down, we see it at great scales on the program level, but we see it at our level, and it does impact us. And I'm sure you heard. I mean, NASA went through a reduction of workforce in the last few months. Volunteer departures of quite a bit of people decided to leave, some of them on my team. And so we had to rush and replace those people. That's a disturbance, that's a risk to the mission, and we live with it, right? It's you do your best. The fortunate thing for us through the Artemis program is that the Artemis program is one of the highest priority of the agency. So despite the overall reduction of NASA budget, the Artemis program actually budget went up because we're trying to get to the moon, and so we are one of the offshoots of Artemis. So we get the required funding we need. So from funding perspective, we were okay. From staffing perspective, we lived through the same as any program. Where we saw colleagues have to leave or decided to leave. The reshuffle of the use of contractors also affect us because we use a lot of contractor workforce. But again, we live with that environment and try to push through. Yes.
So one of the questions you answered, kind of, because you asked a different question, but came to the same answer. What I was going to say, what is the from what you learned with the seismology? I've got two questions unrelated. What kind of decisions will be made based on the data that you learned from that this unit captures?
So there are two aspects to it. Again, there's the science and the exploration. From the exploration, within few months, NASA will ask us, okay, what is the seismicity of the South Pole? Can you tell where are the areas that are quiet on the South Pole? Where are the areas that are shaken all the time in the South Pole? We will be able to provide that answer, and we'll provide it at the first 3 months, we'll provide it after a year, we'll refine it after 2 and 3 and 4 years. By the way, there is no lifetime to the station. It's gonna keep running until a component will break. There is no consumables in the station. So we take solar energy and we just keep humming. That's the first question. So the seismic hazard, what is the seismic hazard? And that is a requirement for us to provide an analysis to the agency. The second one is what's the micrometeoroid hazards at the high altitude? Is there a meteor shower we don't know of that basically once every year comes in and it just mow the lawn on the South Pole? And so we need to understand those type of things. But then from a science perspective, our goal as scientists is to try to understand the structure of the interior structure of the moon, which tells us how the moon formed. That gives us a bigger question of putting in context how the moon and Earth formed 4 billion years ago. And that's not a deliverable to NASA as an agency, but more of a deliverable to the science community. And that's gonna take data for years, possibly a decade. Students and PhD students working on that, and a lot of theses, a lot of work, a lot of papers published to get there. We're only providing the data. We will provide the data that will be archived for years where people can work with. For the last 50 years, we still see publication came from the Apollo seismometers. So that those 7 years during which the Apollo seismometer worked on the surface, they provided enough data for people for half a century worth of research. And so that's the hope.
So, I almost answered this next one too, from a robustness standpoint, related to solar wind or coronal mass ejections, did you take that into consideration?
No, not really. Our biggest, once you put us on the surface, there are our biggest threat is the actual starship leaving the ground. So the crew will put us 100 meter, 200 meter away. But as that vehicle is going to start ascending, it's going to just blow a lot of plumes around, and that's going to mobilize a lot of dust particles. And so what you see here in gray is actually ballistic material. It's like a Kevlar, a material called Nextel. That's a ballistic shield, so it can stop projectile. But we're not immune from, a 1 centimeter pebble coming at, a bullet speed that will tear a hole in us. So that's a risk that's been quantified and it's accepted. If we survive after the HLS leaves, then truly the only threat we have is either a component, a piece of electronics will die. Your TV, you had it for 10 years and one day you turn on, it doesn't turn on. And so that's a natural failure of sporadic failure of a component, or an act of God. I mean, a micrometeoroid just decide to hit that exact spot and just tear you apart. And there is nothing we can do about it. But then again, the probability, most likely, we are going to die. The instrument will cease operating because just the component failed. We are fairly closed. We don't care about, we're not susceptible to coronal mass ejection or flares and the beauty of the lunar environment is fairly quiet. There is no wind, there is no erosion, there is really very few things that can happen to you. It's a desolate, but a very, very peaceful environment. If you can survive the day and night cycle, kind of live through the heat of the day and the cold of the night, most likely you can live for a long time.
Great, thank you.
Go ahead.
Since you're so close to the South Pole, won't there be lunar days that are totally without sun?
Yes.
And so it will still survive.
Yes. So that is one of the issues in the South Pole. So if you deploy this in the equatorial region or mid latitude, it's fairly deterministic. The sun will rise, will stay in the sky for 15 days, and will disappear for another 50 days, come back. The South Pole, the moon is a little tricky because the axis of rotation, the axis of rotation of the moon is almost vertical to its orbit. And so and the plane of rotation of the moon around Earth is just few degrees off the ecliptic. And so pretty much everything is vertical. And so the sun at the South Pole will rise just a few degrees above the horizon and then set. And so it's very, then topography starts playing a big role, because if the sun only rises a few degrees and sets by a few degrees, then it takes a little canyon in front of you for the sun to never set. You see it there. It never went away. And it takes a little hill in front of you for the sun to never rise, because it just went up by a few degrees, and the hill, the view and angle of the hill is just a few degrees. And so there are regions on the moon where you never see the sun rise, even if it's just there behind the hill. And the regions where the sun, where you are a little bit on the hill, where the sun goes down, but doesn't go down deep enough, and you still see it all day long. And so there are areas on the moon where it's day permanently, and there are areas on the moon where it's night permanently. And so we're designed to be able to sustain ourselves for about 25 days of consecutive nights. Okay. And after those 25 days consecutive night, we only need 2 days of sunshine to charge the battery. And then we can take another 25 days of consecutive night. And so as we work through the site selection for landing, we're trying to look for locations that do not exacerbate our condition beyond that 25 days of darkness where we're running on our own energy, but give us a couple days to take a breath and recharge and go back again. And so, but there are areas where you don't want to, you may not see the sun ever, or the sun is there all the time. Okay. Thanks.
All right. Dr. Benna, what a fantastic, excellent presentation. We have a few more items to go through here, and then hopefully we'll have some time if people want to come up and take a closer look at the model here. So let me see if I can get this back up and running.
And as a reminder for those of us scoring this place all the time, that we do need to get moving out of here at 9 o'clock. So
Yeah.
the kid folks want to go home and work here.
All right, stop that.
And Jim, I think you were asking about Matthew Peters. It looks like he's online again.
Okay, we'll see if we have a chance to circle back to him. I'm trying to, why is this doing this? All right, let's go back. There are times when I really hate Microsoft.
Stop updating.
Oh, that's not going to work. All right, we're just going to do it this way then.
What are you trying to just roll it up?
I want to get the full presentation.
Is that what we see on the
Oh,
screen?
I'm seeing something. All right, I'm seeing something totally different here. Okay, guys. So for shallow skies, we've got Saturn coming up at opposition this month on the 21st.
Jim, you're not sharing on Zoom?
Okay. I'm going to Zoom. Share. Okay, does that have you, Wayne?
Yep.
Alrighty, so Saturn
Yes.
opposition, which basically means it rises at sunset, sets at sunrise, so it's visible the whole night. The rings, this particular operation, are not open very wide, but it gives you an opportunity to view the globe much more closely than you would with the rings being open. Also, because there is less glare from the rings, you're going to be able to see some of the fainter moons in your telescope, like Mimas or Enceladus. So, there we go. So on the night of the 21st, at just around midnight, so from the 20th going into the 21st, there's going to be like a parallelogram of moons off to Saturn's side there. You'll have Tethys, Dione, Enceladus, and Mimas. And again, this is not something that, with the rings this thin and the glare cut down, you have a much better opportunity to see this sort of a gathering. Once the rings begin to open up, this becomes very hard, kind of large telescope territory before you could see something like that. Jupiter is also getting to be pretty well placed. It's rising at about 1:30. The two equatorial bands appear to be pretty broad. They did not disappear during solar conjunction. The south temperate belt down here is very thick in some parts, very thin or absent in others. And reports of the Great Red Spot are that it is still reddish and about the same intensity as last year. One thing of interest is that we're entering a period of double transits. Most of you, if you've observed Jupiter, and you can see it with almost any size telescope, when the moon's cut in front of the planet, they cast their shadow on it. We're now, because of the resonance of the moons that are locked in an orbital resonance, about every 1.25 years, you get into a period where they lock up and you will see two shadows or two of the moons crossing at the same time. So I would refer you to Sky and Telescope. I'm not going to make it. Sky and Telescope for October. And you get a few months of being able to see these double transits. And then finally, the thing that I really want to point out is that on maybe just read it. September the 19th, early morning. Get out there and take a look at this. It's going to be well done. It's going to be a very thin crescent moon, Regulus and Venus. Seriously, this should be a very, very awesome conjunction or appulse. So I'd really recommend setting the alarm going out. And if you are a night sky photographer with just your camera, this will be well worth trying to take a picture of. It's only going to be 1.5 degrees from the moon to Regulus, and then Venus will be there too, making a triangle. So that should be pretty stunning. It'll be low on the horizon, so you need a good eastern horizon, but that should be pretty magnificent. All right, so now we're on to photos. And the first one here this evening is by our own Phil Whitebloom.
So I tell you, I'm going to just highlight a couple things real quick because I could talk about this for half an hour easily. This was magnificent to look at. I mean, what you're looking at there is several seconds worth of images. That's about 25 images I think I put together for this. But there was so much stuff. And you look in the middle there and you see some of those whiter spots, the plages. The day before, these were flaring. The day after this image, they were full on CNEs that made the news and lit up the auroras soon after that. If you look on, I posted this picture, I sent it out to the club, and there's quite a long description that I wrote with everything that's happening here. I have to tell you, I've been studying the sun since 2012 pretty regularly, and this was one of the most exciting viewing sessions I've ever had, period, to watch how much was happening. I watched over hours. And eyeball, you know, the imaging. The nice thing about solar imaging is you get your pictures done and you go back to the eyepiece. And it was changing, and just take a look. If you have the picture, if not, I can resend it out with all the descriptions on the Flickr site. But it was just tremendous to watch how much activity there was. And the picture came out great. It took me about 5 hours to process this one. To pull it all out. And I was done with a 60 millimeter H alpha scope. So you don't need a lot of aperture. I did use a Shorty Barlow, a 2X Shorty Barlow, to bring me in closer. But it just came up right. And there was nothing really going on around the edge. So sometimes, it's not as dramatic as when you see a giant flare happening like right before your eyes. That's always cool. But this chromosphere image is fantastic. So I'm done. And you just look at the filaments and the horseshoe shaped filaments and all that other stuff. I zoomed in on some of those. I have other images I haven't posted yet because we're processing them. But when you get in close and you see the 3D impact, when I have some of those other images I'll put up over the month, it's so cool.
Yeah, amazing. Thank you, Phil. Okay, Rich, are you online? Okay, so Rich went out to the Almost Heaven Star party. I think that's West Virginia, with his C8. And this was some of he's a fairly new astro-imager. And this was the dumbbell nebula that he took. As you can see here, that's about 24 minutes of integrated time with a color camera. Pretty darn good. He was almost a little hesitant to show it. I said, no, this is really great work, especially if you're early on in your learning curve. And he also submitted this with NGC 7331, the Deer Look group. There's other little galaxies around it. If you were to zoom in here, you can actually see the supernova that erupted there just beginning to fade out, but you can still make it out near the core. So again, this one about 40 minutes of light integration. Again, a great start to an astrophotography career there. John, I know you're online. You want to tell us about this beautiful image?
Yeah, this is the elephant's trunk. Probably a pretty often imaged nebula object, but I haven't done it with the current equipment that I have, and this was a single night, 5.6 hours just recently. I finally got the equipment back out after not having it out almost the whole summer, and in 1 week I had two good nights.
And speaking of which,
and this one I'm very proud of. It's an object in the Cygnus region of the sky. So there's a lot of other objects here. Just out of frame from this area of the sky would be the Crescent Nebula. It's like, I think it's called the Satyr region. There's a lot of hydrogen, the red in this picture. And this was the first time I imaged it. The main blue object just off the center is Wolf-Rayet. It's a nebula caused by a Wolf-Rayet variable star, which I believe is the blue one, just about the center of that circle there. And yeah, I never imaged this object before, and it came out really well for just one single night. I imaged in both hydrogen and oxygen.
Awesome.
I submitted this one for an APOD, but I've yet to hear back. So I'm crossing my fingers that it gets accepted. There's only 3 other images of this one when I searched the APOD database. So
yeah, it certainly looks APOD worthy to me. That's for sure. Thank you. Okay, this one's mine. We recently had Mercury's morning elongation in August. And this is one of the tougher targets to image. So this is Mercury on the left there. The right is like simulation software, WinJupos, in terms of what the surface was kind of showing. So you can see, I mean, not a great bit of detail, but you can see there's like a dark Maria region there that I'm picking up. This general darkness here seems to be, reflected here. So I was, and this was captured during the daytime. So, yeah, this is the best I've ever done with capturing Mercury, and I felt really, really good about that one. So, Harini, can you come off mute? You want to tell us about your contribution here?
Yeah, so this is the moon. I took this on I think it's 7th of I don't know when I took it, but it was a crescent moon that day, and it was a really nice moon actually. You can see the craters.
Very nice. And you did that with your sea star.
Yes, I did it with my sea star.
Cool. And now, from something close by to something quite far away, which was this?
This was the Pinwheel Galaxy. I took this for 61 minutes. I learned that it was discovered by Pierre Machon, and it was added to the Messier catalog. It's 21 million light years away, and it has about 1 trillion stars. The galaxy contains 1 trillion stars, and its apparent magnitude is 7.9, and it's located in the constellation Ursa Major.
Very nice. Very nice. Thank you, Harini. Appreciate you sending them in.
Thank you.
All right, Ken, are you online?
I'm here.
Oh. Take it away.
That's the Omega Nebula. It's with a newer telescope of mine, a 6-inch carbon star. And it's I went to Cherry Springs for my first time ever. I took this from there. It's just oxygen and hydrogen. I did the sulfur didn't come out very well, so I just put the oxygen and hydrogen together, and that's what I ended up with. You can see the swan in the center, but it's a lot more gaseous than a lot of the images show of it.
That's beautiful.
And that's that interstellar comet. It's going by really fast, 130,000 miles an hour actually. Each shot is taken 2 minutes apart. You can see it moving.
When you sent that in for a brief second, I thought it's going through the Pleiades, and I'm like, no.
And that is cool. And my friend had a 20-inch telescope, and we could find it through it visually by finding that little Pleiades of star there.
Wow.
But it was like 17th magnitude, so it was pretty faint.
Yeah, that's pretty cool.
It's not the
Our interstellar visitor.
Nuclear power spacecraft. And that's another shot of the Deerlick group.
Beautiful. I love the dust lanes that you got captured in that. It's gorgeous.
Incredible.
Wow. All right. We are up against the clock here, so I think we're going to bid everybody a good night. Our thanks again, Dr. Benna, for a wonderful presentation. And remember, guys, second Thursday of the month next month, and different venue in this classroom. And I hope to see more of you next month at the next HAL meeting. Thank you very much.
Well done, Jim.
Oh, thank you. Let me take this off.